Comparative analysis of our sun solar temperature models, traditional fusion theories versus the unified theory of U. Abstract. This paper provides a comparative analysis of the traditional nuclear fusion model of the sun against a new theoretical paradigm presented in the book The Unified Theory of U, which posits a fundamentally different mechanism for solar phenomena based on the dialectical interaction between the sun's subtle magnetic field, SMF, and the relative vacuum of space, RVS. This analysis critically evaluates both the theoretical foundations and the empirical support for each model, particularly focusing on their explanations for the temperature distribution within the sun. Introduction. Conventional solar models based on the theory of nuclear fusion describe the sun's energy production occurring at a hypothesized high-temperature core of 15 million degrees Celsius. These models face challenges, particularly in explaining the anomalously high temperatures of the solar corona and low temperatures of 6,000 degrees at the sun's surface, and then suddenly the temperatures rising to over 15 million degrees at the sun's core. In contrast, the unified theory of U offers a theory based on the dialectical interactions between the SMF and RVS, proposing a mechanism where only the sun's corona is heated by the interaction between the SMF and the RVS, creating a plasma field responsible for the high temperatures observed in the corona. Overview of traditional solar models. Core temperature, estimated theoretically at around 15 million degrees Celsius. Surface temperature, photosphere, directly measured at approximately 6,000 degrees Celsius. Coronal temperature, observationally confirmed to exceed 1 million degrees Celsius, with peak temperatures in some areas reaching 2 to 3 million degrees Celsius. The unified theory of U, alternative solar model. This model is predicated on the theory that the sun's most intense temperatures, particularly observed in the corona, are not a product of internal processes, but result from the dynamic interactions between the sun's subtle magnetic field, SMF, and the relative vacuum of space, RVS. These interactions at the outer boundary of the sun are theorized to create a plasma field due to the significant pressure differential between the SMF and the RVS, challenging traditional notions of solar temperature dynamics. According to this model, the interactions between the SMF and the RVS at the solar boundary drive the temperatures in the corona to extreme levels, ranging from 1 to 3 million degrees Celsius. This range is consistent with empirical observations and highlights a departure from traditional models that hypothesize a cooler surface and a hypothesized hotter core, which, according to the book The Unified Theory, U, all planets and stars are hollow by design. The elevated temperatures of the corona are explained through the plasma field, generated by the intense magnetic interactions at the boundary between the sun's magnetic field and the cosmic vacuum, or RVS. This approach diverges significantly from traditional models that rely on nuclear fusion and supplementary mechanisms like magnetic reconnection. Traditional models fail to coherently explain the drastic temperature differential observed, from a hypothesized core temperature of approximately 15 million degrees Celsius dropping to around 6,000 degrees Celsius at the surface and rising again to between 1 and 3 million degrees Celsius in the corona. The unified theory of U addresses these discrepancies by proposing that the intense interactions between the subtle magnetic field, SMF, and the relative vacuum of space, RVS, at the corona are sufficient to explain its high temperatures, offering a more coherent and theoretically robust explanation for this solar phenomenon. Comparative analysis, empirical observations, and theoretical consistency. Traditional models rely heavily on established physics but require complex additional hypotheses to explain discrepancies like coronal heating. The unified theory of U integrates both direct observations and a robust theoretical model explaining these phenomena through magnetic and vacuum dynamics. Predictive power. Traditional models offer detailed predictions based on nuclear processes. The alternative theory, while newer, suggests novel, testable predictions regarding the behavior of magnetic fields and their interactions with the vacuum, which could potentially be verified through advanced solar observations. Conclusion. This comparative analysis highlights the need for a nuanced understanding of solar physics, positing that traditional nuclear fusion theories do not adequately explain solar phenomenon, and alternative explanations like those proposed in the unified theory of U provides a theoretical model that not only aligns with empirical observations, particularly for coronal temperatures, but also offers a fresh perspective on the fundamental dynamics at play in solar phenomena. This theory challenges the scientific community to broaden its theoretical frameworks, to include interactions between magnetic fields and the vacuum as primary drivers of solar behavior.